Thank you all for joining, and thank you, Ted, for accepting to present. Thank you again. Ted is working in LLM research. He had a PhD in cognitive science with Tom Griffiths at Princeton, and he worked in Anthropic, and he is currently in Princeton University. And he wrote, together with other colleagues, a very interesting paper last year called CoALA, about a general framework for language agents. And so I thought it would be good to have him present his work in our seminar. So thank you again, and the stage is yours.
Awesome. Thank you so much, David. As David alluded, this is a piece from about a year ago when AI agents were, I would say, more nascent than they are today. I think things have advanced somewhat. And so it's actually interesting to kind of go back and look at some of the perspectives that we had in this paper. I'm assuming everyone can see the slides. I actually am going to be in full screen mode, so I unfortunately can't see if folks have hands raised. So please just feel free to speak up with questions. I'm very happy to stop and kind of talk at any point in this presentation. Okay, awesome. So as I'm sure everyone's aware, the basic paradigm of a language model is, you give it some input text and it produces some output text. And so the sort of standard autoregressive mode is, maybe you put in today is a good and it auto completes day, or, who was the US president in 1970 and you get back an answer. Or maybe you query it for some knowledge. And actually, ironically, I haven't gone back to these slides, but this would now actually be supported by most modern models. But you might run into the sort of like knowledge cutoff date for a given LLM. Now, obviously, things get more interesting when the language model can interact with the world in some meaningful way. And so that's the basic paradigm behind a language agent, where instead of taking the output to be a piece of text, and the input to be some piece of text and the output to be some piece of text, you can take an observation from some external environment and feed that into the language model. And then you can interpret the language model's output as specifying some action in the real world. And this lets you put the language model into essentially a feedback loop with some external environment, enabling it to both take actions to influence the world and then sort of observe aspects of the state in order to guide its decision making. So that's the basic idea behind a language agent. And this plays out in a lot of ways. You folks may already be aware, but there's quite a bit of work around using language models as planners in embodied robotics. So this is CoALA, which was an influential early system that basically looked at the sort of tasks proposed by a language model and then sort of the robotic agent state to see how probable it was that action would succeed, and then essentially did planning by intersecting those two. As well as systems like generative agents, which is essentially a sandbox environment that has these sort of individual agents that are being run by a language model and can follow a consistent personality and go out and sort of explore the world in this really rich and interactive way, and both learn about the world and update their own beliefs and have quite rich interactions with each other. And one of the really exciting things about this generative agents paper is that they actually have a fairly advanced internal state representation for the agent. So it has some set of perceptions, and it's sort of organizing those into what the agent itself has done in the past, and then sort of what that reflects about its long-term beliefs and desires and things like that. So that's great. These are, sort of a handful of examples from a increasingly large literature, as well as a lot of examples in practice of these advanced systems that are being run by language models. I think another notable example that's worth calling out down here on the left is Voyager, which was a very impressive and advanced Minecraft agent about a year ago. And then obviously today, there's other systems like OpenAI's Operator and Deep Research and things like that, or Manus, which are sort of more advanced real world AI agents that are grounded directly into users' computers or the internet, as opposed to sort of more academic proof of concepts that were all the rage when we wrote this paper. So that's great. Language agents are obviously cool. One of the big challenges with this space, though, is that there's a whole, gigantic set of concepts and sort of environments that you can employ the agent into, as well as techniques to improve the agent's behavior, with feedback or self-reflection or reinforcement learning directly. There's a lot of different ways to organize the sort of storage of information, to manage the control flow of the agent. You have questions over whether it's a human in the loop setting or multi-agent. And so it's a very fast moving space that's actually like very difficult to sort of wrap your arms around in terms of like what exactly are the differences between different agent architectures, or what does it mean to have something like memory in an agentic system. And so this paper was actually an attempt to sort of go into the history of cognitive science and explore similar concepts there, in particular the idea of a cognitive architecture, then apply that idea to sort of modern language agents, to sort of ask whether aspects of cognitive design might be helpful in the language model era, and then sort of ask what, given that sort of view of agentic systems, what are we missing today? Like, what are the design principles that we're not actually drawing on, or sort of negative space in terms of what's not being looked at in the literature? So this is a fun paper because it takes us all the way back to the sort of classic cognitive science era, where people were working with production systems. So production systems are actually grounded in logic. They're basically sets of rules. If a certain condition applies, then Y must be true. And one of the really cool things about production systems is that they're a model of universal computation. So you can, in fact, express anything that you want in a production system in a series of these logical rules. And so this was picked up in the symbolic AI era, most notably by Newell and Simon initially. And they have this sort of famous example of a thermostat agent, which is a super simple agent that basically applies a series of these if-then rules. So if the temperature is between 70 and 72 degrees, that's Fahrenheit, which is a comfortable temperature, then the system stops and says, things are good. I don't need to take any actions. On the other hand, if the temperature is below 32, something has gone really wrong and it should sort of call for repairs. If it's less than 70 and the furnace is off, then it should turn on the furnace. And if it's greater than 72 and the furnace is on, then it should turn off the furnace. And so this is just like a super simple little agent that's going to actually sort of look at the state of the world and take an appropriate action in order to regulate the state in an acceptable band. And so this basic idea of a production system actually enabled quite sophisticated symbolic AI agents. They built up this sort of conditional decision making by just organizing the sort of priority over these rules. They enabled interaction with the world via various input and output modules. And they were able to access and store knowledge in various memory modules. So the most famous examples are SOAR, which is on the left, and ACTAR on the right, which is SOAR is more of an AI architecture that was explicitly designed to sort of enable these advanced artificial systems, whereas ACTAR on the right was much more intended to sort of mimic the structure of human cognition and serve as a basis for experiments. So people pushed this quite far, and they were actually able to get fairly complicated sort of robotic behaviors and things like that. But they ultimately ran into these challenges where the world is extremely complex, and so you cannot specify like a full production system that's going to enable effective behavior. And in addition to that, the world is inherently stochastic, and so this sort of deterministic rule application really ultimately didn't pan out in terms of like delivering open-ended behaviors in the real world. And that led to this, long period of sort of AI winter where artificial intelligence was like a little bit of a dirty word, and there's a freeze in funding, and there essentially was very little work done on cognitive architectures in this 35-year period or so. Now, I think the really interesting thing is we're back in an era where these systems seem plausible. And one of the really cool things that motivated this paper was the realization that at the end of the day, these two systems are doing something very similar. You have some input, some state of the world. It gets processed by either a very simple sort of Boolean lookup thing, or it gets processed by an autoregressive language model and it spits out some output. And in fact, what we show in the paper is that language models are actually formally equivalent to production systems. They're actually a limited subset of string manipulators which do append-only operations on the input. And so you can actually see a language model as a large stochastic production system where instead of defining a sort of single if-then rule, it defines a distribution over possible actions in possible string continuations in the real world. And so these issues that we faced where the world is too complex and you can't specify all the rules, as well as the world being stochastic, and so this sort of set of rules is never going to work sort of well enough for edge cases, those actually start to look much more tractable when you pre-train a language model on the internet, because functionally what you're doing is getting an extremely useful prior. That is an extremely useful initial distribution over possible outputs given some input. And so this sort of realization that language models are in fact production systems motivated us to go back to the literature on cognitive architectures and ask what it might look like to sort of take this basic concept and translate it into a sort of language model based system. I'm going to stop for a second and just say, before we dive into the sort of specific aspects of the CoALA architecture, any questions from any of that, or any, I don't know, concerns about this sort of claim that language models are formally equivalent to production systems? That's controversial in some areas.
Like, can you say a few words about how you can prove that LLMs are formally equivalent to production systems?
Yeah, so ultimately a production system is really a set of string manipulations. Like I've described it as specifically logical operations, but in fact, it really is like taking an input. You take an input string, and the production system tells you how to modify that input string. And so it's really, there's not a mathematical proof in the paper. It's actually just literally showing that the functions that an autoregressive language model implements are in fact string manipulation, and that it is simply a subset of possible string manipulation, like quote unquote rewrites of the string, which are always append operations. So given some input, the output is an append operation onto that input, and that is by definition like a restricted production system. Does that make sense?
Yes, sure. But well, it's a way to relate LLMs to symbolic systems, but would it say that LLMs are part of symbolic systems?
There are not. That's an interesting question. I think what I would say is you can implement a symbolic manipulation with an LLM. It's not, obviously you can't make the claim, it doesn't have the logical structures, and so it is manipulating symbols in some sense. It's just not doing it in the classic logical framework. It's doing it in the weights of the language model in a way that is difficult to access explicitly.
Yeah. Okay, thank you.
Yeah. So essentially, maybe that's a better way to phrase it. Language models are being used as production systems, or they're being used as a form of symbolic system, or they're being used for the same tasks that we attempted to use symbolic systems for 35 years ago. Okay. Any other questions before we move on? Cool. Awesome. Okay, so what does it look like to actually sort of build this set of sort of structures around a language model in order to enable efficient and effective real-world action? So in CoALA, we adapt and sort of apply three main concepts to language models. The first is some notion of memory, that is how the agent persists state over interactions. The second are the actions themselves, that is the sort of action space that's available to the agent. And then finally, the third is a decision-making process, that is how it uses its state or manipulates its own state in order to choose a certain action at a given point in time. Okay, so first we'll talk about memory. So the first kind of memory that I think is useful and important to distinguish is working memory. And that's the information that the system has available for the current decision cycle that is loosely equivalent to the context window of a language model. So you can think about that as the sort of immediately available information that the language model will use to make a specific short-term decision. The second form of memory is long-term memory. And this is, I think, more interesting and breaks down into a couple subtypes. The first is the procedural memory in the system. And that breaks down into both the weights of the language model itself, that is the knowledge that's baked into the language model, as well as the code that's used to scaffold these interactions. So everything that the agent does to sort of actually operate its decision cycle is, written in code, and that constitutes a form of procedural memory. That is the knowledge of how to do things in the world, how to take a certain action, what it means to call a certain function. Those are all sort of elements of the system's procedural memory. A second important form of knowledge is semantic knowledge. And this is actually facts about the world. So knowing who the NBA champion was in 2023, knowing who the current president of the United States is, knowing what the sort of state of the economy is. These are all facts or information about the world. And the third important kind of memory is episodic. This consists of trajectories or sort of specific experiences that the agent itself has had in the real world. In the sort of most naive form, this would be the actual raw transcripts from rollouts, or just like a chunk of the agent's history in sort of raw form. Does that make sense to everyone? Any questions about these different forms of memory? These are all, I should add, these are all grounded in cognitive science and sort of the literature on psychology and neuroscience. They were originally adapted from that literature into cognitive architectures, and we've then adapted them further into cognitive architectures for language agents.
I would have a question. So if the working memory is akin to the context, or like the context length of the LLM, for systems such as like retrieval augmented generation, which dynamically calls something back into the context, where would you locate the information that can be called back into?
Yes, so it's a great question. So a RAG database would be semantic memory. And so that's actually a great segue to the next kind of broad area we'll talk about, which is the action space. So I think most people, when they think about language agent actions, they think about these sort of external grounding actions that the agent is taking in the world, whether that's producing an utterance in some dialogue setting, or actuating some motor in a robot, or making a call to a website, or otherwise taking some action on a computer. Most of the time when people talk about actions, they mean these kind of external actions. But one really important observation for these more sophisticated language agents is that there's actually a whole very rich set of internal actions that the agent could take to manage its own state. And so these internal actions consist of actions like retrieval. So RAG would be a great example, where you have, let's say, you have a RAG index over your semantic memory, and the agent might be asked a question like, who is the NBA champion? And it might know that based on its weights, but it would be safer to make a RAG call out to semantic memory and try to pull in factual information that it can ground its answer in. And so it might first take a retrieval action to pull relevant information back before producing a dialogue action. Does that answer your question about how RAG plays in here?
Yeah, it does. Thank you.
Cool. Yeah, absolutely. The second really important thing that it might do with its memory is to choose to learn something. So maybe it experiences something in the world, like a particular, it has some episodic rollout, and it decides that that's a really interesting rollout that it should save into its episodic memory. And so it might actually write that episode into some database. Or maybe in the process of that rollout, it decides that it's learned something important. Maybe a user has expressed some particular preference, and it wants to commit that to its semantic memory. And so it might actually choose to write that back to its backing database, so that information is available for future decision cycles. And finally, another super interesting internal action that the agent can take is reasoning. And so reasoning is obviously, in the time since we wrote this paper, reasoning models have themselves become a big thing. One of my co-authors, John Yu, was the guy, he's the lead author on React and a bunch of other, like Tree of Thoughts, a bunch of other of these sort of reasoning systems. And so we at the time felt reasoning was a super interesting and underutilized behavior, because it's actually just the process of generating additional tokens in order to update the system's current context. So you're not pulling in facts from the world, you're not pulling in additional information, you're actually just sort of processing the information that you already have available in the context in order to improve your decision making. And that was particularly interesting because there really was no equivalent action in production systems. Everything else that we've talked about to date, that's all drawing directly from the literature on production systems and just thinking about, how would that play out again in the modern RAG world or things like that. But reasoning is something that really has no parallel in the sort of like or no direct parallel, I should say, in the symbolic production systems literature. Okay, so at the end of the day, these retrieval and reasoning actions support decision making. That is, you're going to pull some additional information into your context, or you're going to do additional processing given what you have in the context in order to improve the quality of your subsequent actions. Whereas learning or grounding are outcomes of decision making. That is, the system should decide to commit something to memory, or it should decide to take some external action in the real world. Okay.
Sorry.
Questions? Yeah, please.
Like sometimes in maybe not in language agents, but in agents in general, you would have the possibility to make simulations like using a world model. So
yes.
Why didn't you integrate this here?
That's a great question. We talk about it in the paper a little bit. I don't have anything about it in the slides, but you're totally right. Having access to either, so one thing that you can do with language agents is you can literally just sort of do reasoning in order to sort of do a forward rollout where you reason about hypothetically what would happen if I did X, Y, or Z. But there also is a literature on these integrated like simulation systems where maybe you run some Mujoko simulation, or like you actually run a more complex simulator, like a quantitative simulator. Depending on exactly how you architect the agent, that would most likely look like from this diagram, that would look something like a reasoning action, but it could also be thought of, and in fact, SOAR has an explicit physical simulator module. It could be thought of as an independent module that does stuff like that. So this where is it called out? Maybe it's not called out in this version, in this particular diagram, but there is actually a it's not in this diagram. There is a specific physical simulator module in SOAR that is used to do exactly that, and it's definitely an important part of the sort of more abstract agentic reasoning capabilities.
Okay, thank you.
Yeah, absolutely. Okay, and that's actually a good segue to decision making, because we'll talk about the different mechanisms that you could use to choose an action. So the default, something like the sort of say-can system that's like largely stateless, is essentially to propose an action and then take it. So there isn't really a serious consideration of like alternatives. An alternative is to actually consider multiple actions in parallel and then ask, how good does this action look? And sorry, actually, I should say say-can is more of this latter. It simultaneously proposes all possible actions, evaluates them against value functions, and then takes the one that looks the best. But you could also imagine a more sophisticated agent that's actually doing simulation of possible outcomes, whether that's simulating in text with reasoning, or simulating by writing a little program to simulate what it thinks is going to happen, and then sort of rolling it out quantitatively, and then looking at the actual outcomes that it thinks are going to result, and then choosing an action based on the outcome. And so in order to sort of encompass these varying levels of sophistication, we propose a generalized decision cycle that you can conceptualize as broadly having a planning phase where the system is doing reasoning and retrieval to propose, simulate, and evaluate actions. And that sort of looks like this little loop where the system gets some observation. It does a planning process where it's retrieving information, evaluating the possible actions it could take. And then finally, it selects an action and actually applies that in the real world, which leads you back then to a new observation and a new round of planning. So this is deliberately very high level. And one of the reasons that we wanted it to be high level is that this whole framework then allows us to characterize existing agents as being sort of partial implementations of the very broad CoALA framework. And so just to give you a sort of working example, we can go deep on this generative agents paper and look at how the system that they built can actually be described very effectively in the sort of CoALA framework. So if you read the paper, you'll see that they talk about how agents store this complete record of the agent's experiences, which then synthesizes into memories using in sort of higher level memories. And so this is clearly consists of both a long-term memory that has episodic information, that is the actual record of the agent rollouts, as well as these sort of derived semantic insights on the basis of those interactions. So periodically, these agents will like reflect and think, what did I do today? Did I have a good day? If I did have a good day, what did I, what actions do I enjoy? What interactions do I have with other people? Are they my friends? Things like that. And so this process of reflection on memories is actually driving the consolidation of information from episodic, which is like very raw transcripts, into semantic or more sort of compressed, distilled facts about the agent itself or about interactions that it's had in the world. Generative agents, engage in these sort of very rich interactions. They're doing things like waking up and cooking breakfast, and then sort of remembering and reflecting. And so we can see that the action space of one of these agents can be understood as having multiple forms of grounding. They can have dialogue with each other. They also have a sandbox world that they can take actions in. And they also have a really rich set of internal actions that allow them to retrieve memories, commit new memories, reason about the memories that they have in context in order to guide their actions. And then finally, they have this sort of nice decision loop, which actually winds up breaking down into just a repeated loop where they retrieve a set of memories, they propose a new action on the basis of those memories, they take that action, and then they reason about the results of that action and can choose to commit things to memory on a sort of preset schedule. And so it's a fairly structured and cyclical decision process. They don't have a lot of flexibility about when to choose to learn something, but it nonetheless implements like a fairly comprehensive sort of basic loop over all of these actions. And so one of the contributions in the paper is that we go back and we look at all of these agentic systems, and we actually can break them down into having different forms of memory. So for example, these early systems, the robotic say can thing or the React system, they actually have no long-term memory. They're purely operating over the language model's context. A system like Voyager, which can actually write new functions for itself, is actually able to update its own procedural memory. So it can not only execute a function, but it can actually like write to that memory. Generative agents are particularly interesting because they're the only agent class at the time that could actually do this more advanced episodic and semantic learning and retrieval. You can also consider the sort of context that the agent is deployed into. So say can is a physical system, it's grounded into the real world, whereas the other systems are predominantly digital. And then you can look at the internal actions that these systems can take. So something like say can has no internal actions. It's literally just proposing a set of possible actions, and then sort of combining the probability estimates from a language model with the value function learned by the robotic component. React is capable of reasoning, so it can do limited updates to its own internal state within a context window. But then Voyager and generative agents are much more sophisticated in the sense that they can actually meaningfully update their own long-term memories in order to behave more adaptively in the future. And then finally, we can look at the decision-making loop that these systems have in place. So say can does have this evaluate step, as I mentioned earlier. It sort of produces a prior based on the language model and then reconciles that with a value function learned by the system. So it can evaluate the utility of these actions. But at the time, none of these actually use language models, other than tree of thoughts, use language models to propose multiple options and sort of evaluate the utility of those options prior to choosing a single one. And so at the time, we were very excited about these sort of more sophisticated structured reasoning methods. In the meantime, of course, we've seen the advent of lots of reasoning models from OpenAI and DeepSeek, and of course Anthropic, which are capable of doing this form of reasoning in sort of long form, purely autoregressive ways. Okay, any questions about these sort of existing systems or sort of the application of the CoALA framework to understand them?
Like since the paper, did you saw some new papers proposing new types of actions?
That's an interesting question. I haven't seen any really new. I haven't seen anything that has caused me to question whether the CoALA framework is sufficiently general. If that's maybe what you're asking. I would say I think I can talk a little bit about the ways that today's agents are only doing some of what we discussed in CoALA. But I don't think that there's any sort of radically new actions that don't fit into this framework that I've seen. I'd be curious. Obviously, I think it's kind of interesting. Every time I give this talk, people have different takes on how useful CoALA is. One major concern or criticism of the paper is that it's pitched at too high a level of abstraction, and so it's not actually useful. Or there are lots of questions around how existing techniques sort of can be understood within this framework. But I've yet to hear a particular thing that really falls outside the scope of what we proposed. Again, I would be curious to hear if you have examples in mind. But
no, it was more out of curiosity. Thank you.
Yeah, absolutely. Any other questions? I'll keep moving. Cool. Okay. So the last bit of this is of course, using these insights in order to actually understand maybe where there are gaps in the literature and identify interesting directions for future work. So I think one really interesting conception is sort of the idea that we can unify the concept of learning as some type of writing to long-term memory. So whether you're updating your episodic memory with a particular experience, you're updating your semantic memory with knowledge, you learn something in an interaction, or the system does this process of reflection, or whether you're updating the language model's, actual parameters itself. Like maybe you're going to fine tune the agent should be able to fine tune its own behaviors on some set of episodic traces that it knows are high utility in order to guide its actions. All of those can be seen as different ways to modify the system's behavior in the long term. And you can then start to ask questions around where is the optimal component in the agent to sort of store this information. And then, I think there also, one of the nice things in the paper is that it also revealed a lot of these sort of gaps, like things that people could be doing but weren't. So for example, no systems were actually updating the agent's own code for decision making. And so you might want to have a system that, could learn to use a simulator under certain circumstances. It might learn that its own, natural language reasoning was actually not as effective as running a physical simulation. And so it would actually be able to modify its decision making to take that into account, either by updating the actual abstract decision procedure or by including sort of relevant guidance to itself about how to consider the set of possible actions. Like don't do something in the physical world that might be might involve a fragile object without simulating your trajectory multiple times and sort of doing some kind of risk-aware planning, something like that. And so the paper, I won't go into more detail here, but the paper itself has a lot of sort of call outs of areas that we felt researchers should be focused on. I actually haven't gone back recently and looked at it in light of the sort of most recent wave of deep research and things like that. But I would say my general sense is that people are still not approaching memory in this like principled fashion. Instead, it tends to be a lot more oriented around existing tools off the shelf, and sort of picking the one that's most expedient to them, rather than asking sort of in a more principled way, what does this information really mean to the agent and how should it be used in the long term? And therefore, what is the best way to store it? Okay, so ultimately our contribution was around agent design. It was, the description of a systematic and modular design pattern that allows you to both compare different agents. So say, what is fundamentally different or similar about a React agent versus a Voyager type system, as well as, in industry, potentially reduce technical debt through shared implementation. So Shunyu went to OpenAI to build agents there, and Kartik went to Sierra to build agents there, and I went to Anthropic. And so we never actually did an open source framework for CoALA. This was one of our plans. But certainly in principle, having these sort of like defined modules should enable you to reuse these components across systems rather than sort of rewriting a semantic memory from scratch. CoALA also defines a framework for deliberative reasoning with language and memory. And so again, the sort of generalized decision cycle, it really sort of clarifies the role of long-term memory in decision making and suggests that agents in different contexts with different potential severity of outcomes should sort of adjust their planning process accordingly. and it unifies things like these different forms of learning, as well as this concept that you should be able to mix both language and simulation-based reasoning. Again, that's something that we talk about much more in the paper. Awesome. The last thing that I'll say is there are a bunch of, I think, interesting kind of open conceptual questions which do in fact remain open today. So the first is this notion of like role of memory in decision making, and we do make a fairly strong claim that there should be we should move from this like single shot RAG thing to more interactively retrieving and reasoning over information. And if you look at the behavioral systems like Claude Code, for example, if you've played around with it, I think that those systems actually do achieve a much better balance of like understanding when they should go out and learn more about the world before they take actions. There's kind of an interesting conceptual question of like the boundary between an agent and the agent's environment. So you know, if you think about the case where the agent actually contains Wikipedia inside itself, like its semantic memory contains an instance of Wikipedia, versus having the ability to call the Wikipedia API, those are actually meaningfully different scenarios in terms of the sort of controllability of the sort of data that you're managing, the risk of the information, you know, that you have becoming stale versus the risk of going out into the world and having someone, you know, intercept your API call or otherwise data poison Wikipedia. So there's some element of controllability, as well as how coupled your system is to the sort of structure of Wikipedia versus just having an external API that it can learn to use effectively. There's a question of how agents should integrate the sort of dual processes of learning and acting. And our proposal in this paper is pretty clear, which is that you should view learning as just another action that the agent can take. So rather than having some sort of externally imposed learning schedule or sort of static reflection period, the agent should itself reason about when it is appropriate to update its internal state in expectation of possible future action. So it should be able to determine that a particular thing that happened in the real world was interesting enough to commit that to episodic memory. It should reach a point where it realizes that its episodic memory is sort of maybe too large to wrangle, or there's a lot of things in there that in light of subsequent experience, it actually should, you know, go and consolidate. And so it should be able to go in and do that reflection step itself. As well as things like update its own procedural knowledge. And then lastly, you know, one of the things that we grappled with in this paper is like what changes with more advanced language models. And this is certainly something that I think we still don't really have a great handle on. It is certainly clear that the more capability that the base language model has, the less structure you need in terms of like managing all this context. On the other hand, I think one trend that we've seen with these more advanced models is that the more intelligent they are, the more structure they can effectively manage. And so a more advanced agentic reasoning model is actually going to be better about knowing when it should commit things to long-term memory. And so when we wrote the paper, we definitely had this thought that like, oh, eventually all of this will probably be subsumed by the model, and like, you know, GPT and you should just be able to run purely auto-regressively and get useful behavior. But I would say personally, my take has been advancing more towards the more sophistication in the model enables a more sophisticated agentic framework, and that the model itself should have more control over that framework. It should be given more optionality to choose to learn certain information and things like that. Awesome. Yeah, and at the end of the day, you ultimately are going to need some form of scaffolding in order to get the thing to sort of interact usefully with the real world. So that's all the content I have. I also would, you know, give major shout outs to my co-authors, John Yu, who, as I mentioned now, is at OpenAI now, and Kartik, who is leading research at a company called Sierra that's doing very cool customer support applications of language agents. They not recently, maybe a year ago now, they put out a cool evaluation framework called TauBench, which I think is very cool. And their systems are largely based on the sort of CoALA principles. And my advisor, Tom. Awesome. So that's all that I have for slides. I would love to address any questions that folks have.
Thank you very much. There are people watching on YouTube. If you have questions, post it in the chat channel, and we will read it here on Teams. Are there any questions? Siran, maybe you have your mic open. No.
No, just to say that it was very, very interesting to see a formalized like way of describing all these different components that you see appearing in all these papers. And then recently there was this paper called Titans by Google that that also exhibits a lot of these different memories and ways to call them. And so it was very cool to see an attempt, a very successful attempt to kind of have some kind of nomenclature, or how would you call that? Ontology of such components.
Yeah.
So,
yeah, that's exactly right. And I think, my advisor, Tom, is a awesome dude. And I think one of his takes really on the deep learning era in general is just that there's like a lot of rediscovery of things that people spent a lot of time thinking about back in the day. And certainly the tools that we have now are different in meaningful ways, but also a lot of smart people spent a lot of time thinking about these things. And you can get very far by just not forgetting what we've already invented.
Actually, that brings a question to my mind, which is not about learning and remembering, but it's more about forgetting. Like, how would this happen in such model, aside from catastrophic forgetting, which is just a byproduct of learning more? But let's say that through experience, that there is this information that you used to go through your episodic or semantic memory, you can actually get through an action, like an API call, whatever. How would that look like forgetting?
Yeah, so that's a great question. So if you look at what, I don't know if y'all are familiar with the Claude Plays Pokemon thing that we did recently, but one of the reasons that I really like it is because you can see the agent's actual context management process playing out on the Twitch stream. And so essentially all agentic memory there is done recursively. It has some initial trace that it starts with, a big rollout. Eventually that rollout gets too long. It says, okay, I'm going to summarize this. And then it just sticks that at the start of the context and keeps going. And then at the end of that trace, it says, okay, now I have to summarize this. And so it summarizes sort of the original summary plus the new context. And you're sort of just accumulating, you're forgetting just by compressing into a particular summary. The much more advanced form would be, a system that does something like what the human brain does, where, the reason you sleep for 8 hours a day is your brain is doing consolidation. It's actually taking that time to go back and say, okay, I just experienced a shit ton of perceptual data, right? I don't have the buffer to hold all of that indefinitely. So I'm going to take it and sort of do REM or whatever it is that we actually do when we consolidate memory. And so I think that form of like compression is probably the most interesting form of forgetting for me. Like, you're forgetting the actual circumstances. I can't tell you, I can tell you how to get from my office to my house. I can't really replay for you the 5th time I did that. And that's adaptive forgetting, because I don't need to know that. I really only need to know the procedural knowledge at this point. And so I think that's the thing that really interests me. I think most of the time when people talk about forgetting, they're more like, they think about it in terms of like, what rows in the database should you drop? And I'm like, yeah, that's one form of forgetting. That's an important form of forgetting. But the most interesting form of forgetting is like this decision of transitioning knowledge from concrete into abstract and how to handle that effectively. And obviously the recursive thing works well enough to play Pokemon and go get a couple badges. But I don't think it's going to take us all the way to AGI.
Thanks.
Okay, just because you mentioned it, I'm curious now, what is your take on AGI?
Oh, God.
Yeah, maybe I wouldn't have dared to ask if you didn't mention it, but since you
like, what's my timeline? Like, when is it coming? Or is it a thing? Okay, I mean, so obviously let me just say, all of the content in this talk is purely based on my own PhD research, and all opinions and everything presented are exclusively my own. Having said that disclaimer, I think I just am ultimately one of those people that thinks that that whole AGI thing is just a moving goalposts debate. And that if you looked at what a system like Claude Code can do today, or a system like Deep Research could do, you know, even 10 years ago, I think most of us would have been like, wow, that smells like AGI. And so I think the term itself is pretty overloaded and maybe not super helpful at this point. I think in terms of the, like, when will we get meaningful transformative AI in society and what will it look like? I think this is just purely based on vibes, but my impression, based on seeing things like Manus, which I haven't played with myself, but a lot of people who I know have extensively. I think there's a huge capability overhang even right now in terms of just like integrating these systems effectively into the internet and people's lives, and adequately managing long-term memory, honestly, in order to get them to not go in crazy loops in Viridian Forest and spend 6 days in Mount Moon or whatever. That's just a question of like appropriately processing the system's inputs in order to derive a better conception, in order to situate it within a task, rather than a fundamental limitation of the model itself. And so AGI, can of worms, highly capable AI systems that are doing meaningful chunks of work, that seems fairly plausible to me in the near future.
Yes, sure. Okay, thank you. And
did that answer your question? I'm not actually sure what your question was, but
no, but it was not a precise question. I was just willing to know how do you approach the AGI concept, because as you said, I think it's overloaded and it's difficult to And also,
I would say the last thing maybe that I do want to note there is, like, I personally have a huge amount of uncertainty over how all of the, how like AGI or AI in the next couple of years will play out. I would say that's something that's just like anybody who knows anything feels that way. Like that's not a controversial take. I did recently read. I will do one plug for some Anthropic related material on this, which is I did recently read Dario, our CEO's like Machines of Love and Grace again, the public his public blog post, and I think it's an interesting take on sort of the things that might change in the near future given these sort of highly capable systems.
Okay, and also like because you have a background in cognitive science, in humans, agency is related to intentions.
Correct.
And so, how do you see intentions playing or not a role in cognitive architecture for AI?
Yeah, that's a great question. One thing that we debated a lot was whether it was worth having like a specialized module that held goals. Like, should you privilege the notion of a goal? Because obviously that's sort of the upstream of intentions. We decided not to. We decided that should be best understood as a form of semantic memory, that basically the agent should be persisting some, sort of desires about the way the world should be, and that should be used within the planning process to sort of reconcile with what it believes the state of the world is, in order to derive a plan. Does that answer your question?
Yes.
Yeah.
Okay.
So most of the agents, the best answer is most of the agents' background knowledge about the state of the world, things that aren't directly within its context window, should be stored in long-term memory, and that includes both goals and some estimate of the world state.
Okay. Is there any other questions? I see no hands risen.
Yeah, maybe one last thing about learning as an action, because and when you mean learning as an action, you mean like not storing things in, not learning as an action as it can be done already, like storing things in a system that can then be retrieved, like for a RAG task, but like, do you imagine that the models could change their weights?
Yeah.
Because we now have this human feedback-based reinforcement learning and stuff.
Correct.
How could that? How could you get the human feedback out of the loop and let the weights self-adjust?
Definitely. So I definitely think that that's plausible. So first of all, I think it is an interesting and non-trivial question, and it will depend on the agent implementation and things like that, to ask, like, what form should learning take? So again, you could imagine you might just store an episode in memory and then hope that you rag back relevant chunks later. You might distill that episode into some sort of takeaways and put that in semantic memory, or you might actually fine tune on that episode. Like maybe you do something really good and you're like, actually, that's so useful that I want to bake it into my weights, like all the way down there. And so there's, oh God, I always forget the name of this, but Jeffrey Hinton in his career as a cognitive scientist had a great paper on it. It's called the Baldwin effect. I think it's the Baldwin effect. Yes. So the Baldwin effect basically says that a organism should store information at the appropriate level in its biological learning system. So if the system is encountering a very fixed state across its entire natural lifespan, that's the kind of thing that should be encoded in our genes. Like you should be born with some rough perceptual prior over what the world looks like. Maybe you have like, something that looks like 9.8 meters squared wired somewhere in your brain, because that's just the environment that we've been in for our entire evolutionary history. But you should not like have the location of water encoded in your genes, because that changes a lot. And so the system has to make some intelligent decision about how and where to store different kinds of information. And so they should all be on the table, but the system should be able to decide, based on its operational history and its intended future deployment, where is most appropriate to store that. And it could be, again, fine-tuning itself, fine-tuning a smaller LLM subcomponent, rewriting the way a certain function works to just be like, actually like fix one parameter or make a parameter free so I can, change it in the future. Those are all, at least theoretically, on the table.
Thank you.
Okay. Thank you. Thank you very much all for attending. I think we can close here if there are no further questions.
Yeah, wonderful. Thank you. Thank you very much. Let me say thank you as well for attending. I really appreciate it. And if you have any follow-up questions or whatever, do feel free to reach out. I'd be delighted to chat.
Okay, great. Great. So thank you again, Ted, and see you next week for a new seminar. I don't remember what the topic is. I will try to look for it. The topic will be oh yes, it's spiking neural networks. So see you next week. Goodbye.